So, hello everyone. Let me present you a problem, actually a very big problem, and it's called Ierum's law, and it has been tormenting the pharmaceutical industry for years. So the problem is, the more they invest on drug research, the less drugs are accepted into the market. So that's a big problem. Why is that though? It turns out that animal testing, such as mice, do not translate well into human physiology. So very clever scientists developed these devices called organ-on-chip, which allow to culture cells inside and therefore emulate human organs and human physiology. However, current methods only produce one, two, three of those devices per day, whereas industry needs to scale this up to hundreds. And so these devices currently have a very low impact on global healthcare. And that's where my project comes in, to scale up the production and also increase their biological impact. So we use 3D printing and injection molding to produce devices made of polystyrene. We were able to create very, very fine devices up to 50 micrometers in resolution. But the more important thing is the whole process takes approximately 2 hours and a half, and we're able to scale the production of these devices up to 500 a day, which is a huge improvement compared to traditional procedures. But using this procedure, then, we were able to create more and more complex devices and integrate higher elements, such as porous membranes, and with them create models to simulate both the kidney, the placenta, and even have embryo models being cultured on these chips. So this way, we can show the biological relevance of these devices and also demonstrate how it can be used to simulate human organs and human tissues. But these devices need to be very accurate in order to do so. And so we used also finite element modeling to simulate the conditions of these devices. We've simulated flow and molecular transport. And this way we were able to predict how the chemicals are transported within these devices. And this way also predict how the cells behave within these devices, and therefore have very accurate models of human tissue. So with a very scalable microfluidic devices being produced, compatible with biotissue and very precise delivery of chemicals, is this the game changer the pharmaceutical industry needs to revolutionize healthcare? I guess only time will tell. Thank you so much, everyone.